Some of the biggest questions we face as a species, the kind that could save millions of lives or even protect the entire planet, they feel almost impossible to answer. But what if we had a tool, a machine, powerful enough to actually tackle them? Well, that's exactly what we're diving into today, the absolutely incredible world of supercomputing.
I mean, just think about it for a second. Predicting tomorrow's weather is hard enough, right? Now imagine trying to forecast the exact path and the sheer power of a massive swirling hurricane. You're basically trying to simulate the physics of our entire atmosphere. How in the world do you even begin to get that right? Or, okay, how about this one? Modern engineering. Building and testing a brand new jet engine can cost a fortune and take years. So how do you simulate every single tiny detail? I'm talking everything from the airflow to the combustion to build a cleaner, more efficient engine all inside a computer.
And then there's maybe the most personal challenge of all. How do you possibly sift through mountains of data from millions of patients, their genetics, their records, how they responded to different drugs, to find a hidden pattern that could lead to a cure for cancer? These aren't just thought experiments. These are real problems being solved as we speak. And the answer to how? Well, it's supercomputing.
So how do these amazing machines actually get to work on a problem? Let's take a look by starting with one of the most ridiculously complex simulations you can imagine, modeling our entire planet. So to model the climate, you first have to break the entire globe down into a grid, kind of like a giant digital mesh. Then you run calculations for every single little box in that grid. But it turns out the simple shape of our planet creates a massive headache for computers. Okay, picture a regular globe, right? All those lines of longitude, they all converge and get bunched up at the north and south poles. For a computer, this is a disaster. The grid squares get teeny tiny, which forces the simulation to take incredibly small time steps. The whole model just slows down to a crawl. It's literally called the pole problem.
And this is where the human brain gets really clever. Instead of just trying to brute force the problem with more power, scientists completely rethought the map. One of the most elegant solutions is called the yin-yang grid. It uses two interlocking map pieces that fit together perfectly, and they completely avoid the poles. It's a brilliant geometric fix that solves a huge computational bottleneck. It just goes to show, sometimes the best solution isn't more power, it's just a smarter design.
So, clever designs like that yin-yang grid are one piece of the puzzle. The other piece, just raw, unbelievable power. Because to run these simulations, you don't just need a faster computer, you need a whole new scale of computing. So, the horsepower for a supercomputer is measured in something called flops. That stands for floating point operations per second. It's really just a simple count of how many calculations that machine can chew through every single second. And what kind of numbers are we talking about here? Well, this, 1 quadrillion. That's a 1 followed by 15 zeros. The moment we hit this number of calculations per second, it kicked off the entire modern era of supercomputing. They call it the petascale era. And to really wrap your head around that, try this. Imagine every single person on Earth, all 8 billion of us, doing 125,000 calculations per second, all at once. A single petascale computer does that all by itself, every single second. It's just a mind-bending amount of power. But of course, technology never stands still. Just as the world was getting a handle on petascale power, the next massive mountain peak was already in sight, exascale. An exaflop is a quintillion calculations per second. And that's not just another step up. It's 1,000 times more powerful than the petascale machines we were just talking about. Now, reaching that level of power, it didn't just happen. It actually kicked off a fierce global technological race. You had nations and research labs all over the world pushing the absolute limits of what was possible, year after year. And the pace of this race is just staggering. Okay, check this out. In 2008, IBM's Roadrunner became the first to hit 1 petaflop, a massive deal. But just 12 years later, in 2020, Japan's Fugaku supercomputer was clocked at 442 petaflops. And then, get this, only 2 years after that, the US absolutely smashed the exascale barrier with a machine called Frontier, hitting over 1.1 quintillion calculations per second. The leap in power has been truly exponential. So, what do we get for all this speed? Why are governments pouring billions of dollars into this tech? Well, the payoff is huge. It's about solving some of the world's most critical challenges right now. And just to give you an idea of the scale of this investment, the U.S. Department of Energy's budget request for its Advanced Computing Research Program for 2025 is over $1.1 billion. That's for 1 year. And that money is directly fueling major breakthroughs. And that investment is paying off in some pretty incredible ways. We've got climate models that can now simulate an entire year of our planet's climate in a single day. GE is designing revolutionary new jet engines that could slash CO2 emissions. In medicine, AI platforms like Candle are fast-tracking the search for cancer treatments. They're even building totally new kinds of computers, like neuromorphic systems modeled on the human brain. And yeah, all those massive AI models we hear about constantly, like GPT-4, they were trained using the power of tens of thousands of processors working together, a direct result of this supercomputing race. And look, this isn't just about science for the sake of science. As the U.S. Department of Energy itself puts it, being the leader in high-performance computing and AI is seen as a strategic key to leading the world in, well, pretty much everything, from clean energy and medicine to entirely new industries. So, if this is what we can do today, the big question is, where do we go from here? Now that the exascale barrier has been broken, researchers are, of course, already looking ahead to the next great computing revolution. Right now, the cutting edge is all about combining these giant supercomputers with powerful AI. But the true next frontier is something else entirely: quantum information science. Okay, think of it this way. The computer you're using now works with bits, a 0 or a 1. That's it. Quantum computers work with qubits, which can be a 0 and a 1 at the exact same time. It's a totally mind-bending idea that promises to solve problems that are literally impossible for even the fastest exascale machine on the planet. The ultimate dream here, the grand vision, is to connect all of these powerful tools together. Imagine a kind of super internet just for science, where data from huge experiments, powerful AI, and the world's fastest computers are all linked up seamlessly. It would give scientists everywhere the power to make discoveries faster than we ever thought possible.
The scale of what Willow pulled off is it's honestly hard to wrap your head around. In just a few weeks, it performed 1 trillion measurements. You heard that right. That is more than every other quantum computer ever built throughout all of history combined. It's just staggering. So Google's success wasn't just a single light bulb moment. It was really a 3-part breakthrough. First up, they nailed robust error correction. You can think of it like a car engine that repairs itself while you're driving down the highway. It can fix mistakes faster than they pop up, which means you can finally do stable, long calculations. Second, they immediately put it to work on real-world problems, like analyzing complex molecules in ways we've only dreamed of. And third, and this is the part that literally broke physics, they figured out how to take the pure weirdness of quantum entanglement, that spooky link between particles, and turn it directly into usable energy. And the precision behind all this is just off the charts. The Willow chip is humming along at 99.97% fidelity. To put that in plain English for you, it makes only one tiny error for every 10,000 things it does. That's the kind of reliability that takes quantum computing out of the physics lab and turns it into a genuine world-changing tool. Okay, so this is all super cool for physicists, right? But what does it actually mean for you and me? Well, let me be clear. This breakthrough isn't just some scientific curiosity. This is the starting gun for a whole new industrial revolution. And the impact is going to be felt, well, pretty much everywhere. I mean, look at this list. Every single one of these industries has been slamming its head against a wall for years, limited by what today's computers can do. Whether it's discovering new drugs, designing next-gen batteries, or building truly intelligent AI, those limits, they haven't just been pushed. They've been completely obliterated. We're not talking about a small speed boost here. This isn't incremental, it's exponential. Let's just take drug discovery as an example. A process that usually takes more than 10 years and billions of dollars can now be simulated with mind-blowing accuracy. Think about that. Problems that would take the most powerful supercomputer on Earth longer than the age of the universe to solve can now be cracked in a few hours. And the craziest part? The pace is only accelerating. Just look at this timeline. It took a while to hit that first big milestone back in 2019. Then, just a few years to the next one. But now the big leaps forward are happening practically every year. This isn't a straight line of progress, folks. This is a classic exponential curve, and we are right at the point where it goes vertical.
So, what's next on the horizon? Well, the Willow chip proved the concept works. It's solid. So now the race is on to scale it all up. The next great challenge, the next big prize, is building a machine with 1 million qubits.
And you can bet Google isn't alone in this. A company you might not have heard of, PsiQuantum, has just jumped into the race with a cool $1 billion in funding and a totally different game plan. See, while Google is using these tiny superconducting circuits for its qubits, PsiQuantum is betting on something else entirely, individual particles of light, photons. And they've partnered with called NVIDIA, with the audacious goal of leapfrogging everyone and getting straight to a 1 million qubit system.
I mean, just look at the difference here. This really puts their ambition into perspective. We are not talking about doubling or tripling the number of qubits. We are talking about a jump of thousands of times over. It's a goal so bold, so audacious, that if they pull it off, it could redefine the entire technological landscape.
Okay, so this is where things get really interesting. We're shifting gears from just automating labor to automating peace. The vision literally proposes to end conflict entirely. And how? With a powerful new kind of AI.
And this is it. The proposed tech is called a space quantum AI. Just try to picture this. A supercomputer with 1 million qubits floating in the ultra-cold of space, all linked up with lasers. It's designed to be powerful enough to watch everything happening on a global scale and, as the source puts it, act as the ultimate security tool. I mean, it's a wild idea, right? But what does that even mean in practice? How would a system like this really change global security? What's it designed to go after?
Well, according to the source, its reach would be pretty much total. We're talking about making things like missile and drone wars literally impossible. It would be able to spot and stop terrorist infiltration before it happens, and it would completely dismantle the business models of organized crime, heck, even things like flash mob crime, just by using overwhelming intelligence and force.
Okay, so if you have technology handling all the work and all the security, what's left for us? Well, this vision says it demands a fundamental change in how we as humans think and live. The tech alone isn't the whole story. Our entire society has to recalibrate.
And this slide gives you a brilliant analogy for that. Resisting this future is kind of like a farmer who keeps using a horse and plow long after the tractor was invented. It's about recognizing that a massive fundamental shift has happened, and you've got to adapt to it.
Yeah, this quote really nails it. The idea is you can't just sit back and wait for the good stuff to happen. We, as a species, have to actively learn to live in a new way to really get all the benefits from this tech.
And this ties back to that idea of security. The argument is that in a world where there's no scarcity, where everyone's basic needs are met, stuff is cheap and plentiful, what's the point of crime? The core reasons people do these things would just evaporate. So crime isn't just stopped by force, it becomes obsolete, pointless.
All right, so we've got the robot workforce, we've got the AI guardian. Let's tie all these pillars together and look at the end game. What's the ultimate result of all this?
Well, the economic engine of this new world is what the source calls the ultra factory. Think about it. You leverage that massive robot workforce, and these factories achieve a level of efficiency we can't even imagine today, hyper-efficiency. And what does that do? It drives the cost of pretty much everything way, way down, towards zero.
And that leads to this, the resulting era. Prices drop to dreamlike lows. All that scarcity-driven stuff like crime, it's gone. Global peace is actually achieved. And with all that taken care of, humanity can start looking outward to building peaceful communities on Mars.
So you can see the path laid out here. It's a pretty clear four-step process. First, you mass automate production with all those robots. Step 2, that leads to hyper-efficiency. Step 3, that efficiency drives prices towards zero. And finally, Step 4, that ends all the bad stuff that comes from scarcity. It's a chain reaction.
So what happens when you have a perfect, elegant solution, but you try to plug it into our messy, imperfect world? What happens when a brilliant answer designed to help meets the incredibly complex systems that we humans have built?
And that is the core takeaway. It's such a sharp insight, right? People don't resist solutions. We resist the upheaval. We resist the messy, uncomfortable, unpredictable change that the solution forces on us.
Look at how thick that inertia is.